Welcome! In this episode we will talk about min-max heaps, which are special binary trees that allow constant access to the minimum as well as to the maximum element, which differentiates them from min heaps or max heaps, which only give constant access to the maximum or to the minimum element. We study those trees because in the end we also want to use them in another data structure which is called order statistic trees, where we can make use of the min-max tree or the min-max heap to access data within a sequence based on the ranks of the data very quickly. Let's study the min-max heap first. So what is a min-max heap? Now here you can see a representation of a min-max heap, an example, and you will see that this is a binary tree, obviously, because every element has at most two child elements. But it also has a special property of being a complete binary tree. So the tree has to be filled from top to bottom and from left to right, and only the rightmost elements might be empty. This property we will later on use in order to find a good memory representation for our tree that is not relying on pointers. Another property of the min-max heap is that the minimum is in the root node. So from all the elements in the tree, the root has the smallest value, depending on whatever ordering scheme you are using. And because of that property that it is in the root, we can also guarantee the constant access to the smallest element. Now the second property was that we can also have constant access to the maximum elements. And that maximum element you will find among one of the child nodes of the root element. So in this case it is the 65 or the 80. So what you have to do is you just check for the child nodes of the root. If there's only one, then it's anyway clear what the maximum is, but if there are two, then you want to give back the larger one of the two. And that of course is already constant. Now we have taken a look at the root, we have taken a look at the next level of nodes in the tree. But by definition, a min-max heap is divided into alternating level of min and max. So the root is obviously on the min level, the children of the root are on the max level, and then every next level is either min or max in an alternating fashion. Based on these levels, you can also see that for every subtree, the root element of that subtree is either the minimum of the overall subtree or the maximum of the overall subtree, depending on if the root is lying on a minimum level or a maximum level. Sometimes the levels are also called odd and even, but because of this property that the root of that subtree is either the minimum or the maximum, I find the definition of min and max level much more convincing than odd and even. But in order to give the complete picture, this should also be mentioned. Now, in the very beginning we said that the minimum and the maximum heap is a complete binary tree, and that property we can use to find a memory layout like this. We want to represent the binary tree in Situ, which means that we can just put it into a contiguous sequence of memory. Other representations would be, of course, that you just have a node and you have pointers, and then the pointers point to the child as well as to the parent. That is also feasible, but then your memory is scattered all over your heap. So in order to prevent that, you can make use of this property that it is a complete binary tree, and then you can lay it out like this. So the first element, the root, is also the first in the array, and then next in the array, next in the memory sequence comes the next level, and then the next, and then the next. And then also the computation of jumping from one element to its child element is rather easy. You can just calculate the respective offsets. What we now want to do is, we also want to take a look at an implementation. And if you're familiar with C++, then you know that in C++ there is, in the standard library, already a set of functions, the heap operations, that give you an implementation of a minimum heap or a maximum heap. But in this case, for the purpose of this video, there is an implementation that I prepared for you that looks like the STL implementation. It follows the same naming convention, so the set of functions that you have in the STL that map to the min or max heap are called like is heap, push heap, pop heap, make heap. Those you can use, and they are also templatized, so the data type that you supply doesn't matter. And they're also templatized in terms of the ordering function that you can supply. So because this function by default is generating you a minimum heap, you can also use the overloads where you can also supply your own ordering function, and then you can give, for example, instead of the smaller than, you can give a greater, and that way you turn the functionality of the minimum heap into a maximum heap. So the same scheme is also possible here, even though it will still be a min-max heap because of the alternating levels. But you could also change that the other way around, that the root level is the biggest element, and then the child nodes of the root element are smaller, or the smallest ones in the tree. So the implementation shown here features the same set of functions, also makes use of some of the newer features of C++ like modules. Let's take a look at what is happening here. Obviously, we define a submodule here already. As I said in the beginning, later on we will also take a look at order statistic trees. So the min-max heaps is just a submodule. The other part of the code we'll take a look at in the later video. And then we define two namespaces, but actually they are the same. It's order statistics namespace. One of them we export, one of them we keep internal to our module. The idea is that in the internal ones we store implementation details that not necessarily need to leak to the outside, but in the export, that namespace part, we will define the functions that the user should use. And then we provide the same set of functions as we know from the C++ standard, only we always have the naming convention that there is an mm for min-max heap. So is heap maps to is mm heap, and then similarly the push heap maps to push heap, and there should also be a pop. Yes, it is. And then of course there's also a make heap. The library is completely based on iterators, so if you want to use a vector to store your memory or a list, even though then the memory is not contiguous, but that should be possible as long as your container has random iterators, which is not by default the case for a list. And for every function we also have two versions, one which takes a comparison object, and one which doesn't, but basically the one that does not just internally calls the other one using standard, the less function from the C++ standard library by default. This library is also again available on GitHub. There's also some unit tests attached to it to check all the functionality, so that should also work for you guys. It's based on the CMake and CTest, so if you download and you have those tools available, then you can just use it. It uses part of the C++ standard library, like the math headers, the functional and the iterator. In terms of the implementation details, there are some some functionalities to do some jumping in the tree, like going to the children or going to the parent or the grandchildren or the grandparents. Those are needed because the algorithms that define the push and the pop as well as the make are based on those functions. Then you also have this is min level because you need to know based on the level what you're actually going to do, because your ordering function, which could be less or could be greater, actually changes its elements based on the level that you are. Imagine you want to push down the tree a small element, then you would use on the next levels always the smaller one, or is smaller than. But if you're on a max level, you also actually want to turn it around and you want to use max. But the user can only supply one ordering function, and then of course you need to switch the way you pass the elements to the function. The way this is accomplished is, for example, by using std-bind, and then you have the placeholders to swap the actual elements. Yeah, the algorithms themselves, it is not so special. You can look up the respective university papers where this is coming from. I will also link them to the video, then you can also study them yourself. And for the rest, feel free to also investigate the code at GitHub. There the documentation is also available. In the next video, we'll take a look at how we can use the minimum maximum heap. And a special version of the minimum maximum heap is also the min max medium heap, in order to do fast statistics computations. See you in the next one. Happy coding!